Okay, so this is the second of the 2018 exam feedback videos, still on part B, so global environmental change. But we're going to be looking at question B4. So this was a question all about how the Earth's orbit around the Sun affects climate change. Again, just to recap, this is the mark distribution for this part of the course. As you can see, wide range of marks. So B4 is the kind of the darker of the greens here. Again, a wide range of marks. Some people did very well, some people not so much. So what we're going to do now is going to go through this question and for each of the parts, identify what we were really looking for and some of the common mistakes that some people made. So if we go to the next slide. Okay, so this is the question. Again, it's in 3 parts. Now this time the mark distributions are roughly equal between each of the sections. So we're looking for you to spend roughly the same amount of time on each one. So the first part is basically asking you to describe the types of orbital variability that there are. How do these types of orbital change affect climate? Well, affect the energy arriving at the Earth's surface. And then the last part, which people did quite badly on, is asking for what is the evidence that the external forcings are not the only thing going on in this climate change. We'll come on to look into that towards the end of the video when we get to it at the end. So again, just trying to deconstruct the first part of this question. Okay, so in the question, it gives you some information that there are 3 things that we're looking for here. Okay, so describe the 3. So we're looking for a description of 3 things of the types of variability of the Earth's orbital parameters. Okay, so you can just rewrite that in your own words and think about what we're actually wanting. So what are the ways that the Earth's rotation around the Earth's orbit around the Sun changes, and how do they change? What is it about these different ways the orbit varies vary? If that makes sense. What timescales do they happen over? Things like that could be added as details, which would get you more marks. So just have a look at the kind of things we're looking for. So of course this is a question about Milankovitch cycles, asking you to describe really the 3 ways that the Earth's orbit varies, and most people kind of got at least some kind of description of these down. That there's basically three main ways. The Earth's orbit around the Sun is not circular, slightly elliptical, and that degree of kind of ellipticity, or I guess eccentricity, changes through time. There's the obliquity, or the tilt of the Earth's axis. So as the Earth rotates around the Sun, its axis of rotation, so basically how it spins around every day, that's not perpendicular to the orbit of the Earth around the Sun. It's slightly tilted over. So that's this example here. And finally, there's this mode called precession, which is where this tilt of the Earth's axis of rotation, that doesn't always point in the same direction. That kind of like wobbles around. So the overall, I guess, parts A, B, and C of this question are really asking kind of, how do these things here change? How do these types of orbits? And, how do they help explain or not explain all of this variation that we're seeing in Earth's climate? So we're looking here at the last, it's 1 million years, 2 million years. Look at all this kind of wobbly variability that we're getting through time. Okay, and going through glacials and interglacials. How are these things linked? So just go through part A, the kind of things we're looking for. So basically describing through each of these types of variation, what are they? So I guess explaining that tilt is the Earth's kind of axis of rotation being kind of tilted over here from perpendicular with the plane of the orbit around the Sun. So imagine this arrow here is pointing maybe towards the Sun over here. So kind of descriptions that would be good. How far is it tilted over? How does this tilt change through time? Sometimes it's a little bit less, sometimes a little bit more. So that goes through this cycle of tilting less, tilting more every approximately 41,000 years. That would be an important thing to mention. And then some of these other points that were mentioned on this slide from the lecture, they will become relevant in the I guess part B. We'll come on to that when we get to them. The next part is this eccentricity. So the Earth's orbit around the Sun is not circular, and this degree of non-circularity changes through time on cycles of around 100,000 years. Now, details which you could have added in at this stage or in the next stage on part B, as I mentioned in previous videos, I don't really care that much whether you answer part of B in part A or part of A in part B, or not even write A, B, and C down, just write one big answer. A thing to point out with the orbit around the with elliptical orbits is that as the Earth is going around the Sun, when it gets to the part of the elliptical orbit that's quite close to the Sun, it'll be receiving more radiation from the Sun because it's closer, which is nice. But it'll also be traveling. Where's my mouse gone? It'll be traveling faster in this portion here than it will over here. So this season will be warmer, and this season will be cooler. And we'll come on to which seasons those actually are, or whether this in fact matters for seasons at all later on. And then I guess the last, or the third, it's not necessarily last, there's no particular order to these, it doesn't matter which way around you do them, mode is precession. So this is how the axis of rotation of any kind of spinning object tends to wobble around as the thing rotates. And this means that as the Earth orbits around the Sun, the direction in which this wobble points changes through time. So sometimes the northern hemisphere, so the direction of tilt is illustrated by these red arrows here. So in this case down here, the northern hemisphere is pointed towards the Sun when it's near the Sun, but over a cycle of between 19 or 23,000 years, this direction of the tilt changes. So it might be pointing towards the Sun at this point in the orbit, or actually this point over here. So in this case, the northern hemisphere is pointing towards the Sun. Okay, so that makes it northern hemisphere summer over here, but we're further away now. So it would mean that we're getting a less intense summer and a milder winter in the northern hemisphere. But remember that in the southern hemisphere, this here would be southern hemisphere summer. So this would mean that we'll be getting a much warmer summer. And we'll come on to this kind of what the effect is between summer and winter in the northern and the southern hemisphere fits into part B. So looking on to part B now we've basically described the types of variation in the orbital parameters. I just kind of flip back actually. It might be appropriate as part of your answer to A just to include some quick sketches of these kind of diagrams that help explain the orbital or how the orbit varies. It's not essential, but again, it does sometimes help to include figures in your answers to make particular points which you might want to make as part of your answer. So part B. So now we've described how the orbit of the Earth varies around the Sun. We could now look at part B, which is how does that affect how the energy arriving at the Sun. So we could go through each of the different things: tilt, obliquity, eccentricity. So this is the circularness or the non-circularness of the orbit. Precession, the way it points. How does that affect kind of the intensity of the season? So this is what I was really getting at with this distribution of heat energy. So how hot the summers are, or maybe how long the summers are. Okay, this fits into part of the eccentricity. And are these changes the same in both hemispheres at the same time? Okay, hopefully you remember from the lectures that for some it is the case and some it's not. So a common mistake that quite a lot of you made was to talk about this kind of effect that we get more energy at the equator than at the poles. Now that is true, but that's not due to the Earth's axis being tilted over or the orbit around the Earth. It's because the Earth is spherical, and the sphericity of the Earth doesn't change with the orbital parameters. So whether this is kind of relevant to kind of, you know, the high latitudes being kind of more seasonal, and having kind of a lower kind of incoming radiation per unit area of the surface, it's not the main answer to the question. So it's kind of like maybe a useful extra explanation, but it's not the main answer. So quite a lot of you missed out by just writing about this, which was correct, but not the answer, which is kind of what we're looking for. Looking at all these three modes of orbital variation. So I guess a good one to start out with might have been explaining how the tilt affects radiation arriving at the Earth's surface. So the more tilted over this axis is, the more extreme the seasons will be. So if you imagine if the sun is somewhere over here, so the northern hemisphere is tilted away from the sun at this particular point in its orbit. So that means that we're going to have it'll be winter in the northern hemisphere here, but it will be summer in the southern hemisphere. Okay. Now, when the Earth kind of rotates around half an orbit, then the northern hemisphere will be pointing towards the Earth, towards the sun, and the southern hemisphere will be pointing away. So it'll be winter in the southern hemisphere, summer in the northern hemisphere. Now, if we increase the angle of tilt, that will increase the kind of the extremeness of those seasons, but it will increase that extremeness for both hemispheres at the same time. So because the northern hemisphere is connected to the southern hemisphere, when we turn over the Earth, tilt it over a little bit more, less, then we're going to increase the magnitude of the seasons for both hemispheres. So the important things for the tilt or the obliquity is that it's responsible for there being seasons, and the more you tilt it over, the more extreme those seasons will be. Okay, so that's the important thing, and that affects the northern hemisphere and the southern hemisphere at the same time. So when we have a year that has a very, very strong seasonality in the northern hemisphere because we're tilted over a lot, which means we're also tilted over in the southern hemisphere, so we're going to get extreme warm summers and cold winters in both hemispheres. Okay, so now moving on to eccentricity. So this is this circulus of the orbit. So the more elliptical the orbit is, so the closer we will be at this point down here. Now, that doesn't make it summer. Okay, so some of you made the mistake of writing down that when the Earth is close to the sun, that's summer. When it's far away, that's winter. So that's not the case. So you can, because you can imagine that when the Earth is close to the sun, it will be, in this example, the Earth is pointed towards, the northern hemisphere is pointed towards the sun. So it actually, in this example, it happens that it is summer when we are close down here, but it's winter in the northern hemisphere. Sorry, in the southern hemisphere. So it can't be winter and summer at the same time in both hemispheres. So what the effect of eccentricity is that if we have a very eccentric orbit, very elliptical, then at some point during the year, we will be close to the sun, and those seasons, whatever those seasons happen to be, will be warmer, or if it's a winter, it might be milder, but you could say a warmer winter. That's also fine. Whereas if we're far away, on the other side of the orbit, the other half of the year, then we are further away from the sun, and that season will be colder, whether it's a colder summer or a colder winter. So that's the effect of eccentricity. It also has an effect on the length of the seasons. So because of the way that elliptical orbits work through Kepler's law, which kind of, it's not really important that you know the details of, but the outcome of that is that when we are close to the sun, the Earth moves faster. When it's further away, it moves slower. And the effect of that is that makes these seasons, whatever they happen to be down here, so in this example here, they're spring and summer. This example here, they're winter and spring. That makes those seasons shorter. So in this example, in the northern hemisphere, it might be warmer because we're close to the sun, but those seasons will be shorter. So that we might get warm but short summers and then long but cold winters. So this effect of the length of the seasons and the amount of radiation received in those seasons kind of cancel each other out, which is kind of, I guess, interesting. So the overall effect of eccentricity is quite small on the total annual radiation received at any one latitude, but it does have effects on, when that radiation is received throughout the year. So it kind of concentrates it into one season, basically. So lastly, looking at precession. So that precession basically determines which way this axis of rotation points with relative to this elliptical orbit. So you can see at the moment the northern hemisphere is pointed towards the sun in between spring and summer. In this example, it's pointed in between spring and it's pointed towards between spring and summer. It's when the Earth is pointed, axis of rotation is pointed directly towards the sun, like this. That's kind of the I guess the summer solstice, beginning of summer. So at this point, we are having warm northern hemisphere summer and a mild southern hemisphere winter. Now, as this red arrow rotates around, some point through the precession cycle, it might be pointed in a different direction. So it might be, in this example here, it's pointed towards the sun here. So we're basically on this kind of average situation where the spring, so the summer and the winter are neither particularly warm nor particularly cold. If you imagine if we were over here and the northern hemisphere axis of rotation was pointed towards the sun here, we would have a milder winter and an extreme cold, milder summer, so a less hot summer and an extremely cold winter. So kind of a little bit complicated whether it's winter, summer, winter, summer, winter, summer. But hopefully you can see that the effect of precession is to also change the magnitude of the seasons, because it determines where in this ellipse summer or spring happens for a particular hemisphere. But the important point is that it's different for the southern and the northern hemisphere. So whereas the axial tilt, when you tilt that over more, you will get a warmer summer in both the north and the southern hemisphere. But with precession, you will get a warmer summer if you're at the closest point to the sun when the Earth's axis is pointing towards it. But in the southern hemisphere, summer will be around the other side of the orbit, so it will be further away and therefore cooler. So a bit complicated, lots of things that to be mentioned here, but they're all kind of collected on the slides in terms of the magnitude of the seasons. It's in phase for the northern hemisphere to happen at the same time. It's out of phase for precession. Those are the things we were looking for. So the last part of the this question was really asking you to think about how we actually get from those orbital forcings to the actual climate change we have. So the question is, what is the evidence of that these external forcings alone are unable to explain the magnitude of climate variability over the past millions of years? So to kind of rewrite that in my own words, although the first one was also my words, but a different way of saying it would be, so we've had glacial interglacial climate cycles over the various timescales, but we get a cycle every 40,000 years and 100,000 years. Also, we get shorter term variability because of precession, but we get some variability on hundreds of thousands of years, tens of thousands of years timescale. And these are related to the orbital forcings. So the question kind of implies that this is true. What is the evidence that the external forcings alone? So the question implies that the external forcings from these orbital variability cause climate change. So that's given in the question. But the important thing that hopefully you remember from the lectures is that the timing of these climate changes matches very well with the timings of the changes of the orbital forcings. but the magnitude does not. Okay, so if we actually look at, well, we'll look in a bit at some graphs, but the question is asking, what is the evidence that we have that there must be some other control on climate other than these orbital forcings that can, allow us to explain the actual climate change record. Okay. So this is the kind of the some of the figures from the lectures. So we've got these variations in these orbital parameters through time. So we can see the eccentricity changing over quite long time scales, precession changing over slightly shorter, these kind of tens of thousands of years, and then obliquity, the axial tilt, that varies on time scales of about 41,000 years. Now you can kind of, at any one latitude, these will have all these different orbital parameters will combine together to give an amount of radiation that place on Earth is receiving through time. And you can see here, here's an example of 65 degrees north. We can see that this is what the Earth is receiving in summer. Okay, and then if we look at a climate change record, here we can see that where we have a intense period of incoming solar radiation, those correspond to these big climate changes, okay, as recorded in some climate proxy. So again, this is really just setting up the question. We're seeing that orbital forcing, okay, is responsible for the timing of climate change. But if you look at the magnitude of these climate changes, so this is a big climate change, this is maybe a big warming here, but this curve at the top does not look like this curve at the bottom. Okay, so if it was a very direct forcing relationship, we would expect if this was the only thing that mattered for climate, then the climate record should look like the forcing record. Of course, they don't look the same. So the question really is asking, what is the evidence that there must be something else? And I guess the first piece of evidence is that this curve does not look like this curve. Okay, that's one piece of evidence that we have. We can also look at other kind of ways of looking at these data. We can see that actually, if we look back further through time, okay, so the question was asking about the past million years, but the orbital forcing has been approximately the same through most of kind of Earth's history, the magnitude of the changes in eccentricity or precession or obliquity. And we can see that over some periods in Earth's history, we have very different climate variability than we do now. And there's been no change in the kind of the types of orbital change from maybe 5 million years ago to 1 million years ago. So this means that the difference between here and here cannot be explained by orbital forcing alone. There must be something else. So that's another line of evidence that the forcing alone can't be responsible. You could have also gone into, the question is asking, what is the evidence? So what is this evidence? What is this climate record constructed from? So you could have given some details about where we get proxy records from. So that was bringing in another part of the course, from the second lecture, I think, about proxies. Where do we get these lines of evidence of climate change from? Okay, so that's kind of what we're looking for in this question. This last part was really kind of trying to stretch you a little bit and asking you to think about the scientific process of going from a theory or a hypothesis of orbital changes cause climate change to testing that with data. Really. Anyway, so that was question B4. Again, answered slightly better than B3, as you can see on these distributions here. But again, hopefully you'll see what we were looking for in this question and where you maybe missed out on some kind of potentially easy marks by just not knowing the types of orbital variability, or not knowing the details of what they actually are, not knowing their time periods. All of these would have scored you perhaps more marks. And importantly, how those variations link to modes of climate change. In terms of tilt causes there to be seasons. More tilt, more extreme seasons. Precession also causes there to be seasons, and determines the magnitude of those seasons, but it changes them differently in the northern hemisphere and the southern hemisphere. Eccentricity affects the effect of precession. So high eccentricity, we have a bigger effect of precession, we have bigger changes seasonally, but overall effect of eccentricity kind of does by itself cancel out, because the length of the season and the being closer to the sun during that season kind of cancels each other out, almost, not quite, but almost. Anyway, so hopefully this has been helpful, informative, or I don't know, mildly productive for you to watch this. Yeah, so look out for the next videos, which will be in for part D, which will be the biogeochemistry cycles. Also, if you've not looked at part B3, the other question for this part of the exam, even if you've not answered it, have a look at it, because knowledge is power, I guess. Right, okay, I will now stop recording.